we go into ray tracing. Up to now, we had been very theoretical, and we just had nice equations that we knew derive them on a piece of paper. In a realistic system, we generally have multiple components interacting, like two metasurfaces who have different distance with respect to the imaging plane, with respect to each other, or a hybrid system consisting here of two metasurfaces. Then there's a classical lens in between. This is much more complicated. On top of that, a real application demands that you balance different trade-offs specifications, for instance, the spectral performance versus view. But this is exactly the domain in which ray tracing excels, and we can optimize this in ray tracing using parameterized waveforms, for instance, with a polynomial series. That gives us the advantage we can co-optimize this. We can design hybrid systems. We've seen a couple of nice talks already today that hybrid systems allow you to correct, balance the aberrations of one component to the next. It's something that optical designers are very skilled at. Of course, we can investigate these complex trade-offs that exist within our system. The disadvantage is these wavefronts are idealized, so they don't take into account generally the errors that come from the fact that your transmission of surfaces meta-atoms is perfect, that you have phase approximation errors. And it also doesn't take into account the limitations that are imposed by your meta-atom material system. But we can take this idealized wavefront and import it back into optical software and approximate it using meta-atoms. So here's the wavefront that we imported with a reference system of silicon pillars designed for near-infrared light. Here you see the point spread function as calculated ray tracing. We then see the point spread function here as calculated using the actual meta components, using the actual structures, their shape, and actually post-process it. Their MTF is the same. What happens is a bit of the light due to efficiency loss in transmission and sampling. As a final example, I want to spend a bit more time doing a more complicated design of this fiber coupler. So we're having two multimode fibers, one here on the left, one on the right, where we want to couple a maximum of light from here into that next fiber, which is a well-known problem, of course, over the entire spectral band of the C and L, from 1530 to 1625 nanometer, the numerical aperture of the fiber of 0.4. So our goal is we want to have minimal coupling loss over the entire spectral band, both with our classical design and with our metasurface design, and also minimize fall. This can get bulky. By the way, the data I took on these as a reference are coming from this link here, which I recommend quite to read. And we're going to do dispersion engineering here. And for dispersion engineering, we need to separately optimize. We need to find a different wavefront for each wavelength. Just to a single wavelength optimization, we get with the problem that all diffractive lenses have, that the longer wavelengths focus closer to the lens themselves, and the shorter wavelengths further away. This first order law. Have different wavefronts for each wavelength. We can actually correct that. That will tell us which dispersion engineering we need, but there's a problem here. We only have a certain band of dispersion engineering available, and for that we need to feed. I have to go further here. Actually, we need to feed the limit of our structure library into the ray tracing to come up with a design that realistic demands of dispersion engineering system. But first things first, we're comparing here three systems. The top is a reference system consisting of our fiber on the left, then an aspheric lens made out of PK7 glass, then symmetrically the same system to couple back into the lens from this free space region back to the fiber. Second possible solution is a hybrid system where we have a metasurface here, a spherical lens on the other side of the surface, and then again symmetric third solution, the dual metasurface, where we have the fiber, one metasurface here, a small one, a larger one here. Going. Here we have our ray tracing solutions. If we compare here the reference, we lose about 0.6 dB on average over the entire spectrum. It's shaking. I'm hitting the thing. Anyway, and the diameter, the volume is around 34 cubed millimeters. If we do a single wavelength meta lens design, a very simplest case, we come up with this solution. It has low losses for the central wavelength, but we actually have high losses for the long and short edges of the band. When we apply our dispersion engineering, we come up with an average loss of 0.4 dB, actually predicted to be below what's possible with the aspheric lens. At the same time, the whole system volume is around 30 times smaller than the conventional solution. So that's great. We now have a design that, at least in theory, produces this nice chromatized beam coupling. We need to take a look at the pitch requirements that we had in this design. If we look at our phase curve from Zemax, we see that we had a pitch requirement to be below 2.5 microns. If you look at our diffraction limit, the sub-diffraction condition for the nanostructures, we see that we need to be below 800 nanometer in size. So we now know where we need to, which limits we need to keep with our lens. We're using here a system of silicon pillars on K7, and we apply our standard routine of creating a library of structures, plotting them here. We're again using these 6 structures and come up with a series of structures here that can cover the phase, dispersion band, and the average transmission. So there's a couple of structures here, especially below the dispersion band, that are very poor in efficiency. These are not used at this time. In fact, the ideal case would be that we have all dark red dots, which have transmission. You see that in a lot of cases it's hard to achieve that. But if we compare this band of dispersion to the requirements that were put on us from the ray tracing design, you see that all over the lens surface, so for the small one, that's this blue line here, and the larger one, the orange one, we stay within this limit. So at least in theory, we can use this structure library in order to create lenses actually meet their dispersion requirements. So that's what we get then here. We have the phase curves for the different wavelengths, 1625 down to 1530. We can tailor the offset in order to shift these differences. That's what you see here, the difference between the red and the blue curve, so that it stays within the band that we have here. See that here for the first lens, we do the same for the second lens. And then run our multi-target optimization. Finally arrive at our set of meta lenses, both for the front and back, which gives you the phase profiles that you see here. So it's discretized to some extent the fact that we have our library. Phase error is low across the entire set design wavelength. So for all lenses, it stays below, near 20 degrees. Phase error for this is actually a little bit better. To improve this further, we'd have to build better and better library, especially increasing transmission level, different steps, phase discretization available to us. And with this, we can generate the GDS files. Then now we start to manufacture for this application. This concludes actually then a design cycle from coming up with the concept and preparing it to reference solutions down to making fabrication files. And with that, I'd actually like to conclude this workshop with the final statement that, in our opinion, to make a true real-world metasurface application, it requires an integrated design workflow from the nanoscale to the component scale to the system scale. That requires in itself then multi-scale simulations in order to do these designs efficiently. You need full wave calculations for the nanostructures, propagation in order to surfaces themselves, and ray tracing to make a system design which has been informed by both the possibilities and the applications of the metasurface. And finally, as you can see, it requires expertise on a lot of different points, from photonics as from optics, to make these designs a reality. Thank you very much, and I hope you all learned something. And if you have any questions, I'm here for you, or you can come talk to me or my colleague Jonas at the say hi to you.